Okay, so in this video, we're going to talk about binomial expansion. And basically, binomial expansion is, taking some binomials and then obviously multiplying them out, which is going to be expansion. And we're going to work through, kind of the long form how to do this, but then also using some simplified techniques as well as like using like Pascal's triangle and so on and so forth. So, and then also, kind of how to apply this. So we'll talk about, how to find different forms or different terms of this, how to solve when we have something that is a binomial, to expand, and then also look at, using completing the square to take an expression and writing it as something squared. So we'll talk about that at the very, very end. So, but let's just go and start off on the warm-up and just kind of get ourselves a little bit familiar with, binomial expansion and kind of see how it can be helpful for us. So, in first example here, I basically have I have an expression x plus y raised to the 0 power, and hopefully with our rules of exponents, we kind of remember that it doesn't matter if you have 3 raised to the 0 power, if you have x raised to the 0 power, or if you have an expression raised to the 0 power. The simplified expression of that is going to be 1. And obviously I don't want to spend too much time getting into, again, those reasons. That's not really the idea of this kind of warm-up, but it is just important to remember that anything raised to the power of 0 is going to represent 1. Obviously, a lot of times we don't even include the number 1 here. We just write something as x plus y, right? But if we raise it to the first power, it's basically just saying, that's going to be the expression of itself. So I can just write this as, x plus y. Now we get into actually the power of using the powers here in 2, because this is saying x plus y times x plus y. So you're multiplying by itself twice. So it's x plus y times itself, x plus y. So what we can do is we can rewrite this expression as x plus y times x plus y. And the sure safe way that I always see students immediately look at this as is x squared plus y squared. Please make sure you do not distribute to the powers. That is not something we can do across addition or subtraction. So do not distribute those powers. X plus y squared represents x plus y times x plus y. Now I'm actually going to multiply this out. Sorry. Okay, so what I'm going to do is multiply this out using distributive property here. X times x is going to give me x squared. X times y is going to give me xy. Y times x is going to give me yx. And then y times y is going to give me y squared. Now, obviously, 3 times 4 is the same thing as 4 times 3, so we can arrange these x and y's the same way we want to, or any way we want to. And that's just going to give me a simplified product as x squared plus, I'll just use the xy. That's going to be, now there's 2 of them. xy plus xy is going to be 2xy plus y squared. Okay. Now let's get into one with cubed. So we already have this. This is going to be, now you could write this as, there's a couple different ways to think about this. You could write this as, x plus y times x plus y times x plus y, right? Well, we already know what x plus y times x plus y is. That's x squared plus 2xy plus y squared, right? So all we need to do now is just multiply by x plus y twice. So in this case, I'm going to write this as x plus y times x squared plus 2xy plus y squared. And again, I'm just going to use the distributive property for this because I think it's, fairly, basic here that we're going to multiply every x times every term and then the y times every term. Okay, so x times x squared is going to give me x cubed. X times 2xy is going to give me a 2x squared y. X times y squared is going to give me a x y squared. And then y times x squared. Now, since that is the same version of this, I'm actually going to put it below it. This is kind of called like the vertical method of adding.
Attention students, this is the last call for students who need to do IDs at this time in B hallway. This is the last call, final call for the day for students who need to take ID pictures at this time.
Okay, and then we have y times 2xy squared, or 2xy, which would be a positive 2xy squared, which is the same term as that. And then I have y times y squared, which is going to give me a y cubed, which obviously does not have any common terms. Now I can just combine my terms, and obviously everything is addition, so it's kind of nice here. But then I get is an x cubed This is going to be 2xy plus x squared y is going to give me a positive 3x squared y. Xy squared plus 2xy squared is going to give me another 3xy squared. And then we have y cubed. Okay. Now for this next one, x plus y to the fourth, that's really x plus y times x plus y times x plus y times x plus y. And I don't really want to write it all out, right? I know that x squared, now I could do this. I could do again what I did in like the last example. I could say x plus y times this would give me x plus y to the fourth, and that's fine. But what I'm going to do is I'm going to do a little bit different method. I'm going to use the box method because you can see, in using this example, things start to get a little bit confusing. You start writing a lot of numbers, and sometimes things can get disorganized. So I could have done the box method over here, but I wanted to show a different method. A lot of times when I'm dealing with trinomials, I prefer to multiply everything by the box method. So, if we just kind of think back into, multiplication and, how and why we use multiplication, the basic idea is, if you have something like a rectangle here, if we want to find the area, we are just going to multiply the lengths times the widths, right? So in the same sense, when we're multiplying, two quantities, we're basically finding the area of a rectangle where we could represent those two quantities as the length of the width of the rectangle. So what I'm going to do is I'm going to break this up as x plus y squared times x plus y squared. Now I already know what x plus y squared is, so I'm going to draw like a line here so I don't get confused, or I don't mix them up. So I'm going to write this as x squared plus 2xy plus y squared times x squared plus 2xy plus y squared. I'm running out of space. Actually, let's. So therefore, I'm multiplying, those out. Now, what I'm going to do, since I didn't really give myself a lot of room, I'm going to rewrite this using a box. I can use this as like a rectangle. You're multiplying those, and they're both. This would actually be like a square, right? Because the side lengths are exactly the same. So what I can do is I can create a rectangle. In this case, it's a square because the length and width are the same. And then for each term of my polynomial, I'm going to create a row or a column. So that. Okay, so again we have x squared plus 2xy and plus y squared. And then the other length, the other x plus y squared, is going to be along the length, x squared plus 2xy and then plus y squared. Okay, so now all I'm going to do is I'm going to find the area of each of these rectangles inside, and the area of all of these is going to add up to the area of the larger rectangle, which is basically just going to be my product, right? So x squared times x squared is x to the fourth. I'm actually going to zoom in one more time. X to the fourth. X squared times 2xy is going to be a 2x cubed y. X squared times y squared is going to be x squared y squared. 2xy times x squared is going to be a 2x cubed y. 2xy times 2xy is going to be a 4x squared y squared. 2xy times y squared, again I'm just doing length times width, 2xy times y squared is going to be a 2xy cubed. Now I'm doing the length and width here of this row and this column. So y squared times x squared is going to be y squared x squared. I could put them in the same order though, that'd probably be better. Let's do that. Just so I'm keeping things consistent. X squared, y squared. Here I have y squared times 2xy, so that's going to be a 2x y squared. And then I have y squared times y squared, which is going to be y to the fourth. So again, this is basically multiplying, this is x plus 1, x plus y squared, and this is x plus y squared, and then I'm multiplying these really to give me the area of x plus y to the fourth power. Now the nice thing I like about this is you can see that on the diagonal, we have common terms. So that just makes things very nice when we're trying to add them up. So I go and take a look at this. I have my first order, or my highest power here. It's going to be x to the fourth. 2x cubed y plus 2x cubed y is going to give me a 4 x cubed y. x squared plus y squared plus 4x squared plus y squared plus x squared plus y squared. Let's see, that's going to give me 6 x squared y squared. And therefore, adding these up is going to give me a 4x y squared, and then I have plus y to the 4th. Okay, so that is basically just the expansion. Now, you can see that the higher and higher values that we get, the more and more work that this is going to take, right? The more and more effort I'm going to have to put into this. So, I mean, this isn't bad. Like y plus 4 to the x plus y to the 4th is not anything like you can't do. But just imagine if it was to like the 14th power, or in the next, or what I'm referring to is like, would you want to do x plus y to the 8th? Would you want to multiply this, you know, by itself to get x plus y to the 8th? And the real answer is no, right? That just doesn't even seem like fun. Unless you just like doing math, then yeah, obviously that work. So what we want to do is start looking at some patterns, and these are the patterns that are going to help us make things a little bit more efficient. So if we look at like the coefficients of our kind of variables, what we kind of do is we start to see some kind of like patterns. Here's one. Like, let's look at the coefficients here. Well, that's really a 1, and that's a 1. Here we have a 1, 2, and a 1. Here we have a 1, I'll underline these, a 1, a 3, and a 1. And here we have a 1, a 4, a 6, a 4, and a 1. Okay? Now, you might not say, well, I'm not really seeing any kind of patterns or anything like that. But that's what we kind of want to do, is maybe like rearrange this into a way that it would make a little bit more sense. And okay, so let's just try to kind of see what happens with these coefficients. So if I kind of create these coefficients in what we call Pascal's triangle, what you can see is I take 1, 1, 1, and then I take the next row, 1, 2, 1 would be the next row of coefficients. Then I do the next row of coefficients, 1, 3, 3, 1, and then I do the next row, 1, 4, 6, 4, 1. And what we want to do is start looking for patterns. And what we start to see is, you can see along the edges, we're always going to have 1, right? And then what we see is consecutive numbers inside of a row, they add up to the next row. Like you can see that here, 1 plus 2 is 3. 2 plus 1 is 3. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. So if this is the expansion of to the 4th power, if this is like, to the 4th, then can we make a hypothesis for what is going to be to the 5th? And yeah, we know that we're just going to add another row of 1s, and then we're basically just going to add the next row. 1 plus 4 is 5. 4 plus 6 is going to be 10. 6 plus 4 is 10. And 4 plus 1 is 5. So now we just found the coefficients, or at least the product of the coefficients. We'll see what happens once we get to different expressions here. But we'll see that at least the scalar of each of these coefficients, or the scalar coefficients here, is going to run. And this Pascal's triangle can be continued. And there's a lot of other things we can investigate with Pascal's triangle, or how we can use binomial expansion. For this case, we're just going to be really kind of focused on its application with polynomials and kind of functions. Now, the next thing I want to look at is, or you to kind of focus on, is look at the powers. And it's really kind of important to remember that, again, x to the 0 equals 1. Y to the 0 equals 1. And that's really important because a lot of times we don't really represent that, right? We don't show x to the 0. But it's important because this expression can be written like this: x to the 1st, y to the 0, plus y to the 1st, x to the 0. And you might say, well, why would I even do that? Like, okay, it makes sense. X to the 0 is 1, y to the 0 is 1. That doesn't change x, x plus y. But why would we do that? Well, the reason being is you can start to see, as we start getting into larger, binomial expansions, we can start to see there's a pattern. What happens here is that first term that we have, that x, as I expand that out, it starts with the power of our expansion. So that's x to the 4th, right? And then in each and every term after that, it goes down in descending form. And it goes all the way down to 0. We just don't write x to the 0, but it's there. The second term is non-existent in that first term. So we could really say it's y to the 0. And then what happens is each and every term after that, it ascends. y to the 0, y to the first, y to the second. Oops, I made a mistake there. That should be that's y cubed. I made a mistake. It should be y cubed. So then therefore that's going to give you y to the cubed, y to the fourth. So our summary here, when we're talking about like, well, how can we summarize this? The x plus y to the powers, so we can say the first term in our binomial expansion, or like when it's in a binomial, first term powers, they descend. And then the second term ascends from 0 to the power of the binomial, expansion. So let's go and take a look at this. Like I'll write this one out again one more time, just so you can kind of see all in there together. So it's, I'll rewrite this expression as with ascending and descending terms. So I have x to the fourth. Again, that's being multiplied by 1. I guess I'll write that in there. Now, notice again, these coefficients, these are multiples. These are scalars. So this is what you're multiplying by. That doesn't mean that because when you're raising something to the fifth power, that's what the coefficients are always going to be. These are just the scalar multiples of those coefficients. So we have 1 times x to the fourth plus 4x cubed, right? So that first term descends. And, oops, I'm sorry. Let's get there. The second term starts at 0, so y to the 0. Plus, the next scalar multiple is 4. And then my x's descend, and my y variables ascend. Plus the next scalar multiple, which is a 6. And then that's going to be x squared, y squared, plus 4. And you can start seeing like the pattern really kind of helps you, write everything out rather kind of quickly. So this becomes 4x y cubed. That's 4 to the first. And then the last one is going to be a scalar multiple of 1, x to the 0, y to the fourth. And there you go. That's a long written out there form. And then obviously here is going to be, you can just kind of go ahead and simplify it. But the main important thing that I want to get with the summary of the expansion using, binomial expansion is understanding the relationship with the powers, what exactly is happening with that first term and that second term, and then as well as understanding what the factor coefficient scalars are going to be for your polynomial. And that's going to be helpful because what we're going to do, obviously, further down is we're going to start expanding stuff and to higher values and to kind of see what exactly is going to be, going on and how can do that rather quickly because multiplying out works, but it's not really going to be the most efficient method. So let's go ahead and get on to examples of using this binomial expansion technique for more binomials.